Hello, everyone. Welcome to today's talk at the Autonomous Seminar. Today's speakers are Kartik, who is a PhD student in visual computing at MIT, and Audrey, who's an undergraduate student at MIT. They will be talking about their paper, Gradient Descent, the Ultimate Optimizer, which shows how to efficiently compute hypergradients to tune hyperparameters of different optimizers. So without further delay, I would hand over to Kartik and Audrey.
Right. Well, thanks, Ria. Thanks for having us here today. So this paper is called Gradient Descent, the Ultimate Optimizer, and I'm not entirely sure kind of what the audience I'm speaking to is. I don't know kind of what background you all have, so I'm gonna give kind of a simple overview of this paper. But at the end, feel free to ask if you have more questions. And I'll start off this talk and then hand it over to Audrey to finish it. So you'll get to hear from her soon enough. I should say, so this is work done jointly with my advisor, Jonathan Reagan Kelly, who's also at MIT, and Eric Meyer, who's at Meta. And we presented this work at NeurIPS this past year. So if any of you were in New Orleans, maybe we passed by each other. All right. Okay. So getting started. This paper is about kind of this funny question, like, can we use gradient descent to improve gradient descent optimizers? And this paper is not, trying to optimize gradient descent optimizers necessarily. It's just trying to improve them. So it's looking for something simple, simple in implementation, simple in idea, something lightweight, online, in fact. It's really thinking about what would it mean to use gradient descent to improve gradient descent optimizers. Well, let's think about how gradient descent works. So when we use gradient descent to optimize the weights of a neural network, what do? Well, we take our old weights and we subtract a little adjustment from it. And what's the adjustment? Well, it's the gradient of our loss function with respect to the weights, scaled by some learning rate. Does this scan for people? Does this equation, like, can someone? Okay, cool. Someone gave me a thumbs up, so I'm gonna carry on. Now here's a question. This alpha, this learning rate, what happens if it's too small? So can one of you just like unmute your mic and tell me what happens if you choose something really small for alpha?
Well, it won't converge, right? So it would just do very tiny update steps.
Right. So it's gonna, these adjustments are gonna be so small that you're just gonna be sitting around waiting forever, and the weights won't change that much, and it'll just be a bad time. All right, someone else. What happens if this step size is too big? Like, what goes wrong? Could someone?
We also don't really converge because we overshoot the target.
Right. So now, like, a different bad thing happens, which is you never really settle into your optimum. Okay, so there's a too small alpha and there's a too big alpha, and somewhere in between there must be a just right alpha, which means that finding the right alpha is its own optimization problem. And I don't think this is new to anyone here, but I really want to kind of state all of this explicitly up front. All right, so in this paper, we thought about what it would mean to use gradient descent to update not only the weight W, but also the step size alpha. All right, everyone good? Can someone who's on camera just like nod to confirm that you've heard everything I've said so far? All right, great. Okay, so all right, so instead of doing the standard weight update, let's do this like souped up weight update, where first we update alpha, which is the step size, and then we update the weights using the new alpha. And of course, now there's this question of what should this adjustment be? So actually, someone who's on camera, do you wanna briefly unmute and give a proposal, or like, what would you choose for this adjustment if you were just kind of looking at this and like thinking out loud? I'm curious.
Well, I would think about like an adaptive approach where I take like the success from previous iterations, maybe. But we could
Yeah,
also use the gradient, right? So maybe.
right. Anyone else want to throw something out there just to get us thinking? Wow. Okay. I guess the answer to that question is no. No one else wants to throw anything out there. Okay, that's fine. So, what adjustment for alpha should we choose? Well, one answer to that might be by analogy to this weight update, we also do some sort of gradient descent step. So we have some like a gradient, and then we scale it by some step size. And in my view, that would look something like this. So you update alpha by taking your old alpha, and then you add this adjustment, which is the gradient of your loss function scaled by this little recursive step size, which we're just going to use the letter kappa to denote that. This is not a new idea, by the way. This is something that was in this, I think, iClear paper by Baden et al. In 2018, but actually you can trace it back to like the 90s and even earlier, I think. And I think it's kind of this nice and elegant way to think about it. All right, so how does this kind of play out in practice? So we want to compute this gradient of the loss function with respect to alpha. What do we do? Well, the first thing we can do is think about, like, if we were doing calculus, like how would we expand this? Well, W's and alphas, like, they're not necessarily commensurate. The first thing we have to do is expand out by the chain rule. Right, so we just chain ruled this W in terms of alpha. Okay, can someone tell me what to do next? So if you're looking at this and trying to simplify this and trying to figure out like a way of thinking about like how to compute this quantity, what's something you might do? Someone who's on camera, do you want to unmute and like give a proposal? It doesn't even need to be correct, just to get some engagement going here.
Wouldn't it need to be recursive or something to include the previous iterations?
Yeah, okay, good. So the key term is previous iteration, right? So another way of thinking about it is like, where does this Wi come from? Well, it comes from something that used alpha in the previous iteration. So let's, expand out where Wi came from. Well, it came from this update rule, right? Like Wi minus 1 minus alpha times some other gradient. Okay, and well, this gradient is actually easy, right? Because it's just a constant times alpha. So, this constant goes away and it's just this coefficient that's left. So in summary, this hypergradient is just the current gradient dot producted with the previous gradient. So this actually like, squares out very nicely. And so, Baden et al. Implemented this and showed that it works, and it was, it was a very nice paper, I thought. Okay, so for simple optimizers, just doing this like standard gradient descent step, things worked out very nicely. Okay, so what happens if we now try to do like a more souped up optimizer? So instead of just taking like naive gradient descent steps, what if we throw in some momentum or something like an atom optimizer? Well, okay, so I sat down and I worked out the math for it, and I have to say it like gets out of hand very quickly. Like the equations get kind of messy, and you have to be really careful about your chain rule, and it's not a pleasant time. And okay, fine, you can say that, well, just do this once and then you're done, and if it's correct, then you've like you've front loaded all the work, but people are always coming up with new kinds of optimizers, and you'd like to be able to efficiently and somehow automatically and correctly derive these formulas. So, the key idea of our paper was, what if we, instead of hand deriving these, use automatic differentiation to differentiate through the update rule? Did that scan? Again, people on camera, can you like nod if you're still with me? Yeah, okay, I got a lot of nods. That's good. All right, so now I'm going to transition from talking about math equations to talking about code. So here's my little like caricature of a gradient descent step. So you've got your like little optimizer, you call it SGD, and it takes a step size as its hyperparameter, and we're calling step size alpha. And what do you do? Well, first you get, to step the weights, first you take the gradients of the weights, you get them from somewhere. And then what do you do? Well, you take the weights and you subtract off the gradient scaled by alpha. Again, this is not like legitimate Python code. This is like my caricature of this algorithm. And okay, what's an important thing you have to do? An important thing you have to do is detach all of these things from your computation graph. Okay, I just said the words detach from your computation graph. Can you nod or thumbs up or something if you know what that means? And like kind of wave frantically or thumbs down if you don't know what that means. And if you don't do anything, I'm going to assume like you're on Twitter right now, which is okay. Okay, but I got some like smiles and nods and I got a thumbs up. So I'm going to assume you know what that means. Okay, someone who's on camera, why do we have to detach stuff from the computation graph? Like, why do we do that? It's, you're all familiar with this as a concept of like things we do. Why do we do it? Yeah, that's a question.
So we don't backprop into the previous iteration.
Yeah, good. I think it's cheating for Audrey, who's an author of this paper, to answer my questions. But right, so if we don't detach these variables from the computation graph, then as backpropagation goes, it's just going to keep flowing through this computation graph we're building, because this gradient descent step ultimately is just arithmetic, right? It's just part of a computation graph. And we have to explicitly tell PyTorch or whatever to truncate the computation graph so that we're not just flowing forever into the past. But for doing hyperoptimizers, we actually do care about what's going on in this little gradient computation. So we have to be a little careful. We can't just go and detach everything kind of with a huge hedge trimmer. All right. Okay. So the first step is we don't detach alpha from the computation graph. We leave the edge from alpha into this gradient computation intact. Okay. Additionally, we throw in this gradient descent step on alpha, and we literally just copy and paste the gradient descent step for W, but replace the W's with alphas and use this new kappa as the gradient descent step size. Y'all with me? People on camera, this is a good time to nod if you're with me. Okay, good. So, all right, now you're looking at this and like your undergrad software engineering lizard brain is kicking in and saying, there's a lot of like repeated code here. There's like these detached statements, and then, these two lines of code are so similar that there must be something deeper going on here. So what do? Well, you abstract, right? You just recursively use a regular SGD to update alpha, because that's all those lines were doing. These lines are exactly the same as what a standard SGD does. So we just abstract that out. Okay, y'all with me? Nods? Great. Okay, and then you think, but really, this isn't quite the most general formulation, because there are other optimizers out there, right? Like, why do we have to force this to be SGD? So as a final transformation, we take the optimizer to use as another hyperparameter, and then we use that optimizer to step alpha. All right, so the way you would build one of these optimizers is that you initialize like a hyper SGD and you give it a step size, but you also recursively give it an optimizer to optimize its own hyperparameters. Yeah, right. And I didn't have to put SGD here. In fact, I could have put hyper SGD here and repeated the process. I could have recursively stacked more and more levels of hyperparameter optimizers on top of each other. And Audrey will talk a little bit more about what that would mean. But okay, so what I've described for you is a way to play with the computation graph to automatically work out the hypergradients for any optimizer. And you just need to really write the forward pass of the optimizer, what it does, and automatic differentiation will take care of the rest. And this kind of careful choreographing of when you detach what make sure that you're not leaking gradients anywhere, and everything is tight and optimal. All right. So okay, that's all I'm going to say about the implementation. I'm actually gonna pause here in case anyone has like burning questions, though with the caveat that if you have like a longer question, maybe wait till the end. But if there's anything like really on your mind right now, now's time to ask. I'll wait for like 10 seconds. 3, 2, 1. All right. I didn't hear any questions. So now I'm going to ask Audrey to talk a little bit about like what happens if you use this thing in practice. And just by way of preface, Audrey is now a third-year undergrad at MIT and did most of these experiments, spent a lot of time debugging these, and really drove the later stages of this project, and is overall an awesome young researcher. So it's like really a treat for you, I think, to get to hear from someone like her right now. So yeah, okay. So with that, Audrey's going to tell you a little bit about experiments, and actually we're going to hand off. So I'm going to turn off screen sharing, and Audrey is going to turn on her screen sharing. Audrey, you're muted.
Yes, I'm muted. Yes. Now does everything look good?
Yes, I can hear
yes,
you
fantastic.
and see your slides. Okay, great.
Great. Yeah, thanks, Kartik, for the introduction. Yeah, so let's take a look at a few experiments that we ran using these hyper optimizers. So the first experiment we ran was we trained an MLP on MNIST with different optimizers. The first observation is that the hyper optimizers generally improve test error over the ordinary optimizer. So you see in the tables on the right here. So this first line is the model trained using an ordinary optimizer. In this case, it's SGD. Down here, it's Atom. And then you can see that the final test error for SGD is 8.99. And then the subsequent lines with the forward slashes are optimizers with hyper optimizers. And then we see that adding an SGD hyper optimizer, in this case, decreases the test error from 8.99 to 4.81. So once again, this shows that adding a hyper optimizer improves the test error over the ordinary optimizer. Second thing to note is that we can sort of mix and match optimizers on the top and bottom, meaning that the hyperparameters of SGD can be optimized by Atom, as here. Similarly, in the lower table, the hyperparameters of Atom can be optimized by SGD. So like the beta 1, beta 2, as well as the learning rate of Atom can be all adjusted together by this SGD optimizer. Lastly, the learned step size often shows a better convergence than the initial human chosen step size. The learned hyperparameters are the value that the hyperparameters end up as at the end of the train run with the hyper optimizer that's shown on the previous line. So in this table, these learned hyperparameters are shown in this pinkish red color. And these are learned from using the hyper optimizer in the previous line. We take these learned values, fix them as constant, and then train using this value. And then once again, we observe that the test error for these values are indeed less than the ordinary optimizer. And sometimes they even do better than the hyper-optimizer. This experiment is then repeated with other optimizers such as AdaGrad in RMSprop, and the same properties hold. Furthermore, we can optimize other kinds of hyperparameters beyond just the step size, such as the gamma hyperparameter in RMSprop, and being able to adjust both of these hyperparameters at once reduces the test error over simply just adjusting learning rate. So the comparison is this line and this line, from 3.55 test error to 3.33. And just as a side note, all of the hyper optimizers that you see in this table were all implemented in less than an hour, which means that it's like very simple to implement this for just like a completely unseen or a completely new optimizer. And what this means is that these hyper optimizers are useful for many different types of optimizers. We next wanted to see whether the hyper optimizers would work on larger networks. So we trained a ResNet 20 on Cypher 10, and in the original paper, the ResNet 20 was trained using a custom learning rate decay schedule where the learning rate is divided by 10 at epochs 100 and 150, which you can see in this graph on the far right. Sort of you have this like giant decrease here and decrease here, which are these like divisions at epochs 100 and 150. So we do three comparisons. So we compare without hyper-optimizer and with this custom schedule, which is the blue line. Then we compare without hyper-optimizer and without schedule, which is the gray line, as like a baseline. And then we just compare with the we replace the optimizer with the hyper-optimizer, and then we get rid of the schedule too, which is this black line. So after doing these three experiments, we find that like the model trained using a hyper-optimizer is able to match or like matches the final test error at 500 epochs around here. And perhaps even more surprisingly is that the adjustments to alpha very closely match the hand engineered schedule if we were to just like draw a point. I mean, not like closely match, but the curve is, the idea is there. It's like trying to do this similar type of decay to the learning rate. And what this means is that the hyper-optimizer like replicates this like optimal learning rate schedule. Now using the same setup, this time we vary the initial values of the learning rate and momentum. So in the graphs on the right, the columns correspond to different initializations of momentum, while the rows correspond to different initializations of the learning rate. They're initialized to different magnitudes, values. First observation is that the hyper-optimizer always converges better than the ordinary optimizer. And furthermore, in nearly all configurations, it matches the final test accuracy of the optimal configuration of hyperparameters. The only direction where this fails to be the case is in these two cells. And in these two cells, the hyperparameters, the momentum and learning rate, are both bad in the same direction, meaning that the momentum is too small and the learning rate is too small. And then the cell down here is both the momentum and learning rate are too large. So learning rate is set to 1, momentum is set to 0.99, which is quite large. So like the main takeaway from this slide is that the optimizer is quite robust to the like the hyper optimizer is quite robust to like the initialization of the various hyperparameters. So even if like when you're training a model and you're trying to decide whether, like, what value to set for your learning rate and momentum, you can be a whole order of magnitude off, yet still achieve like the same performance. Referring back to the Baden 28 paper, they hypothesized that stacking hyperoptimizers would make them increasingly robust to the initial human chosen hyperparameter. And our experiments validate this by initializing the bottom level learning rate to different orders of magnitude. In the graph on the right, the x-axis is the bottom, like the initialization of the bottom level learning rate on a log scale. So this value over here is 10 to the 2, which is 100, and the value over here is 10 to the 8, 10 to the negative 8, sorry about that. And then the y-axis is plotting test error, the final test error after we ran each of these. Similarly, a height of 0, which is the gray line, means that we're just using an ordinary optimizer, while a height of 3 means that we've recursively stacked 3 hyperoptimizers with 1 optimizer. The interesting thing here about this graph is that with the ordinary optimizer performs not quite well for initial learning rates less than 10 to the negative 4. However, when you look at the red line, which is a height of 3, it performs quite decently across a very wide range of different magnitudes. The only caveat is that when you look at initial learning rates set to 10 and above, the performance is sort of bad across the board. But this intuitively makes sense, because with a very large learning rate, values tend to blow up significantly at the beginning. Now we repeat these experiments for a ResNet 20 and an RNN using the same hyper step size configuration, meaning the same pattern of initializations. And we see that the same properties hold in these cases. The height of 3 obtains pretty good results across a wide range of different initial learning rate values. So the top plot here is plotting the ResNet 20 experiment, and the lower plot here is plotting the RNN experiment. And yeah, so it's so like with just the ordinary optimizer, the gray line, it's like for the ResNet 20, it's like not good for this entire range. But when you look at height of 2 or height of 3, it's like pretty flat, and it's like at the same level of as what like the optimal, like, or what the lowest test error is, which is really, really interesting. And then recall from like the very beginning, the first slide, how we wanted something that was both simple and lightweight. We saw that this implementation is simple because you can implement a completely new hyperoptimizer within minutes, but it's also lightweight because each additional level of hyperoptimizer increases the runtime linearly by 1 to 2%. In this graph on the right here, we're plotting like the stack height that we ran for each of these individual experiments. And then on the y-axis, we're plotting the percent increase over the ordinary, like percent increase in runtime over no hyperopt, meaning ordinary optimizer. You can see that this graph is linear, but each interval is only an increase by 1 to 2%. And furthermore, there's like very negligible additional memory usage. And I guess here is the summary slide, just to like wrap up this entire presentation. The main takeaways are that hyperoptimizers are a lightweight and flexible tool for improving your optimizer's convergence. And if you're careful with the implementation, you can recursively stack these hyperoptimizers, which makes them less and less sensitive to the initial human chosen hyperparameters. yes, if you have if you have written questions, you can contact Kartik. I think this is the end of our presentation. We're open to any questions and things like that.